So, Andrea, we cannot hear your voice. It's okay? No, we cannot hear.
Mike, can you hear me now?
Yeah.
I'm just going to mute for a second.
Okay, I think I will just hold the microphone then.
渡辺先生、
はいはい。
多分ホストを、
うん
なんか他の人に移すことができると思うので、
はい。誰にすればいいですか？
じゃあ、アンドレア先生か私でお願いします。
じゃあ、ビルカーさん、今、共同ホストになってるけど、ホストにしていいのか？
はい、わかりました。
So, Maki-san, do you want to do some introduction, or should I just start introducing the speaker and explaining a little bit what we are doing? What would you like to do? Or Eza, or Kosa-san, I don't know who is.
No, I don't mind. It's up to you. Maybe just a very, very short introduction. But yeah, I think we can just go straight in. Yeah.
Perfect. No
so
problem.
So I was saying to Professor Watanabe, I'm starting with some fairly basic things about general magmatic sulfide geology, geochemistry, and then we'll move into the detail. So
yeah, I think it's a good idea.
Should be suitable for
yeah. I think it's a good idea to bring everyone, you know, on the same page. Not everyone probably is super familiar with the magmatic sulfides and so on. Yeah. So do you have an idea how long the talk will be?
It should be about 45 minutes.
Okay. Yeah, sounds perfect. So, Steve, sorry, I was checking your page on the CSIRO website. So your position is called team leader, is that right?
Well, actually, I'm now that's out of date. I've actually recently retired. Okay. So
is that right? Oh, I didn't know.
Yeah. So I'm now post-retirement fellow is my is my title.
Yeah. And you're still in Perth, I guess, right?
I'm still, yes, that's right. Yeah. So I'm still actually working part-time, but officially I'm retired.
Okay.
It's a good reminder. I need to update my webpage.
Yeah, sure.
I look at it about every 5 years.
Sure. This is the CSIRO.
So we have some people working on the Bushweld Complex, yeah?
Yes.
In the talk, Maki-san, you're the one, right? You're the expert.
Yes, I'm working on the Bushweld Complex PG mineralization.
On what aspect?
Hmm?
On what part of the Bushweld Complex?
Eastern limb of the Bushweld Complex and northern part, there is a Limpopo mine. It's owned by Sibanye Stillwater.
Okay, yeah. Is it Merensky Reef, UG2 mine?
That mine is Merensky Reef.
Merensky Reef.
Yes, but my research topic is both of the Merensky Reef and UG2 chromite layer.
Okay. Oh, well, you should, I hope you'll find this interesting then. I think you'll find this interesting then.
Yes. I'm so looking forward to seeing your presentation, and thank you for giving us this opportunity.
Oh, it's my pleasure. Looks like you have another person waiting to join.
Yes.
There you go.
Hello, Manuel. Okay, I see that it's around time. If everyone is ready, maybe we can start. I guess more people will keep coming, but that shouldn't be an issue. Okay, so everyone, welcome to this new talk organized by the SEG student chapter of Akita University. I hope you can hear me correctly. You told me that my microphone is not working very well. So my name is Andrea Aganji. For those who don't know me, I work at Akita. So today we have the honor of having Steve Barnes giving us a talk. So thanks everyone at the SEG student chapter for organizing this, Maki and then everyone else. So Steve just told us that he retired recently from CSIRO, still living in Perth, Western Australia, and still collaborating with CSIRO. And so those of you who are into massive sulfides associated with mafic and ultramafic rocks would probably know his name. He wrote many influential papers. And so today he will tell us a little bit about sulfide melts and sulfide phases in mafic and ultramafic magmas. And then I guess he will focus a little bit on platinum and platinum group elements, if I understand correctly. So Steve, if you're ready.
I'm ready, okay.
And if you want to share the screen, you can start at any moment.
Okay, there we go. So you should have my screen.
Yes, I think we see it.
Okay, great. So right, well, firstly, thanks very much to Reza for inviting me to give this talk. We met in Indonesia a few years ago, and to all of the student chapter, to Maki and others for making all of this work. So I hope you'll find it interesting. So what I'll do over the next 40 minutes or so is give you some general introduction to magmatic sulfide deposits, what they are, and give you what sort of rocks they form in, what sort of environments they form in, and then I'll move into the main topic of the talk, which is trying to understand why the compositions of magmatic sulfide deposits are so variable, and particularly why some magmatic sulfide deposits are nickel copper deposits with very little platinum in them, whereas others are basically platinum deposits with a very minor byproduct, nickel and copper, but all essentially forming by the same fundamental process. So that's going to be the theme of the talk. If you have any questions, please just pop them in the chat as we go along, and I hope we'll have enough time for a bit of discussion at the end. So so let's start right away. If I can get my screen to move, there we go. Magmatic sulfide ore deposits, what are they? Well, they are the accumulation of immiscible sulfide liquids from silicate magmas. They actually comprise some of the world's most valuable ore deposits, particularly the nickel copper platinum deposits of the Norilsk camp in Siberia. On a recent estimate, contain something like $1 trillion worth of metals in that one camp in a small number of deposits. They're the source of basically all of the world's platinum and all of the other platinum group elements, and they're the source of close to 40% of the world's nickel, and that number is probably likely to increase as we go into the future. They're all associated with. They're all basically igneous rocks. They're all associated with mafic, or in some cases, some of the older ones, ultramafic magmas. But most of the deposits we're talking about are associated with mafic magmas, with basaltic magmas, with a few interesting exceptions. So what makes them all? Basically, they are the process of smelting in reverse. So in the process of smelting, we take our ores, we add sulfur to them, we heat them up, melt the sulfide. And the sulfide scavenges the metals, and then we oxidize the sulfide to get the metals back out. But it's that initial process is a process where a sulfide liquid, what's in metallurgical terminology is called a matte, scavenges the chalcophile metals, nickel, copper, cobalt, platinum group elements, and gold from the silicate magma slag. That's a blast furnace, and that's actually a little quench product from the Kalgoorlie smelter, where the West Australian nickel ores are treated. Little blob of sulfide liquid sitting in quenched silicate melt. So that's just a little picture of what the what the system looks like. Okay, where do we find them? A variety of environments going back into Archean and older Proterozoic rocks. We find them in komatiites, extrusive or very shallow subvolcanic. We find them in subvolcanic intrusions and conduit systems in flood basalt provinces, Norilsk and Duluth, the mid-continent of the US being the best examples. In mafic, ultramafic intrusions and conduit systems in plume settings, intracratonic plume settings, where we find them there, they're very often at the margins of old Archean cratons or in intracontinental rifts. And some examples of that would be Voisey's Bay in Jinchuan. They can be at any depth in the crust. Some are shallow, some are very deep. We've recently been working on the Nova deposit in Western Australia, which was placed at a depth of probably 20 or 25 kilometers into granulite facies rocks. So they can be anywhere in the crust. The other major type are magmatic sulfide deposits in large differentiated mafic, ultramafic layered intrusions, of which the Bushweld Complex is by far the most important and the best known, but there are a number of others, including the Stillwater Complex, where there's a palladium mine. And in this case, they're usually stratiform, so they're layered within the layering of the complex. They're stratiform deposits of very minor amounts of sulfide, and they're usually very rich in platinum group elements. Some of the less common settings, although we're starting to find more deposits in these settings now, mafic intrusions in continental arcs, quite a few examples of those. And then the one big exception, the one big sort of outlier and unusual camp in this category is the Sudbury camp, which is a case of a very large meteorite impact, and the ore deposits formed in an enormous impact melt sheet. And in that case, the magmas were actually intermediate to felsic, not mafic at all. But I'm not going to say any more about that. Very rarely, minor amounts of sulfide mineralization in alkalic mafic or ultramafic intrusions, Alaskan type intrusions, and so on. But in terms of the global resource base, these are completely insignificant. Types of magmatic sulfide deposits. Basically, there are sulfide rich ones and there are sulfide poor ones. The example on the top left here, that's a sulfide rich one, where the deposits mainly consist of very, very sulfide rich rocks, what we call massive sulfides, or very heavy disseminations of sulfide, and usually mixed with olivine or pyroxene. Typically, we find these in small intrusions, and these are typically mined for nickel and copper, in some cases for platinum group elements as well, but primarily these are nickel copper deposits. We can also find relatively sulfide poor, but still nickel copper dominant deposits. And the one on the bottom left here, this is from Jinchuan in China, which is actually the world's largest single nickel copper sulfide deposit in northwestern China. And here this is a very typical texture of sulfides interstitial to olivine crystals in a thick pile of olivine cumulates. Now on the right here, this is the type which I'm going to be focusing on in the later part of the talk. These are sulfide poor deposits. So again, just small amounts of sulfide in the rock. But in this case, these sulfides have very high concentrations of platinum. That, in fact, is a piece of the Merensky Reef. So we'll come to that. So basically sort of three subdivisions, if you like: sulfide rich, nickel copper dominant; sulfide poor, nickel copper dominant; and sulfide poor, PGE dominant. But there's a complete mix between them. The mineralogy of these things is pretty much the same wherever you see them. They're all pentlandite, chalcopyrite, and pyrrhotite. That's an XRF map, a nickel copper sulfur false color map. The pyrrhotite's in blue, the pentlandite's in pink, chalcopyrite's in green, and that's that rock underground. Very, very characteristic, and that's exactly the mineralogy that you expect if you cool and crystallize a magmatic sulfide liquid. So how do we make them? Well, basically we form magmatic sulfide liquids when a silicate magma exceeds its capacity to dissolve iron sulfide. And at magmatic temperatures, iron sulfide is molten, at least in basaltic magmas it is. Magmatic sulfides typically, magmatic sulfide assemblages typically have a melting range between about 800 and about 1100 degrees. Typically, the most common way of making these is when we add a large amount of sulfur to a magma by some mechanism or other, more than can dissolve, then that sulfur then forms a predominantly iron sulfide melt and then scavenges the metals. And that's actually a sample from Norilsk there, where we've actually preserved some of the original sulfide droplets that were being carried in the magma. So really there are two ways of getting there. One is to start with a silicate melt, add a sulfide-rich sediment. That sulfide then melts, forms what we call a xenomelt. So that's a sulfide melt, which then reacts with the magma. Think of like a xenolith. This is a xenomelt. It's a xenolith of sulfide, which completely melts. And typically that process causes the magma to crystallize a little bit and also become contaminated. So we end up with a contaminated magma with crystals of usually olivine and droplets of sulfide. Now, the other way we can get there is if we start out with a silicate melt and then crystallize silicates from it, so again, typically olivine. As we crystallize olivine, that drives the sulfur content of the melt up, because sulfur is an incompatible element in olivine. It also causes the ability of the melt to dissolve sulfur to decrease, as the sulfur solubility goes down with the temperature drop. So that causes a sulfide liquid to form. Again, usually together with olivine or sometimes pyroxene, and then we accumulate that olivine and sulfide together into a rock to form our ore deposit. So what kinds of intrusions do we find them in? Well, quite a lot of different kinds of bodies. I mentioned sometimes komatiite lava flows or komatiite subvolcanic intrusions, and then a whole variety of different intrusion types, but there tend to be a few quite sort of common types which contain a lot of the deposits that we find. And a lot of those intrusions are tube-shaped or funnel-shaped, or these kind of unusual morphologies that have come to be called tronoliths. So these are basically tube-shaped sills that are semi-conformable with the rocks that they sit in, and typically contain sulfides accumulated at the bottom. And as I mentioned before, they can be almost anywhere in the crust. So here's a little animation that we made many years ago now to show the formation of magmatic sulfide ores in komatiites. This is a very particular setting where we have a komatiite lava flow erupted on top of a sulfidic sediment. That's the blue unit here. That flow then develops into a tube, into a lava tube. Most of the flux of the lava then concentrates in that lava tube. That causes the rocks underneath the lava tube to get so hot that they start to melt and get incorporated into the lava. Then the sulfide that was in those rocks forms our sulfidic xenomelt, and then that accumulates downstream to form our ore deposit. So this is really kind of the simplest type of process that forms magmatic sulfide deposits. Then in other intrusive systems, it probably gets quite a lot more complicated than that, but that's a pretty good indication of the sort of process. Now, in most cases that we know about, we're pretty sure that the sulfur is actually coming from the country rocks. Some component of the sulfur is coming from the mantle, but the critical thing that makes the ore deposit is the fact that we're assimilating sulfur from the country rocks. And the reason we know that is basically because of the sulfur isotopes, which are in most deposits, not all, but in most deposits are distinctly different from typical mantle compositions and reflect the compositions of the rocks that they sit in. And the best examples of that are Duluth and Norilsk, both of which have very heavy sulfur isotopic compositions as a result of the assimilation of the rocks that provided the sulfur. So now let's move on to what's going to be the main point of the talk from here on, and that is to look at the wide variability in composition of the sulfide component in the rock. So what I'm plotting here, these are two diagrams. One is copper against nickel, the other one is palladium against copper. These are the fields for the compositions of sulfides in different types of deposit. So first of all, I need to explain how we get these fields. So these are not the ore grades. these are the concentrations in the original sulfide component. Now, it's hard to actually measure that exactly. So what we do is typically, for a given deposit, we plot copper or nickel or platinum or whatever against sulfur, and then we extrapolate along that correlation line up to a value of around about 35 to 38% sulfur, which is typically the sulfur content of a pure magmatic sulfide liquid. Then on the assumption that all of these metals were originally collected by that sulfide liquid, that extrapolation then gives us what the original composition of the sulfide melt was. So we'll come back and we'll look at that assumption in a little bit more detail a bit later on. But for now, you have to take my word for it. So what we find fairly typically is that the compositions of the ore deposits depend on the kinds of magmas that they form from. So komatiites are down here, they're typically very high nickel sulfides, relatively low copper. These are log scales. Komatiites have nickel content, nickel in sulfide anywhere up to 30% in the most extreme cases, typically copper less than about 1%. And generally speaking, there's a rough linear correlation. Now we go to more mafic systems, much wider variation in copper. There's also quite a wide variation in nickel, but most mafic hosted deposits that form from basaltic magmas, have nickel to copper values somewhere around about 1 to 1, and they sit in this field over here. Then komatiitic basalts, these are sort of high magnesium basalts, somewhat intermediate. They occupy a sort of intermediate area. And then Sudbury, which I just mentioned in passing, sits here in the middle of the mafic field, interestingly. Now these red spots in this yellow field here, these are the very platinum group element rich sulfides that we find in what we call reef deposits. So these are the PGE rich, low sulfide stratiform deposits, which are mined primarily for their platinum group elements. So the Bushweld deposits will sit in here along with a whole bunch of other ones. Now, the point on this diagram that I want to make is that if you just look at their nickel and copper contents, they're not greatly different from typical nickel copper deposits. They tend to be a little bit higher in copper, and they tend to be towards the high nickel end. But generally, they overlap the field for typical nickel copper deposits, sulfide rich deposits. So in terms of their nickel and copper contents, they're not that unusual. But now let's go over here and look at this diagram. So this is now palladium in the sulfide component against copper in the sulfide component. Here are our fields again for komatiites, mafic, komatiitic basalts, and so on. Now look at the red spots up here, and you'll see that actually they sit out at quite extreme values. Now also notice this is a log scale, and you'll see that the range of platinum group element contents in sulfides extends over 1, 2, 3, 4, 5 orders of magnitude, compared to nickel and copper, which vary over about 1 or 2 orders of magnitude. There's one really extreme one out here on the end. That's the Platinova reef from the Skiergård intrusion. I'm not going to say anything about that. That's a law unto itself. But what I am going to talk a bit about are these very, very, very high ones out here. These very, very high PGE rich sulfides are associated with chromite seams. And that's what I'm going to be driving to at the end of the talk. So now, again, remember the way we get these numbers is by extrapolation. So we take the whole rock content of the ores, we assume that all of those metals were originally present in the sulfide, and then we extrapolate out to a pure sulfide. All right, so what is controlling this big variation? A large part of this variation, as you can see here, is controlled just by the chemistry of the original magma. So if you've got a komatiite magmas are very rich in nickel, very low in copper because they're very high degree partial melts. Komatiites are, to a first approximation, basically just molten olivine. That explains why we have very high nickel to copper ratios in komatiites. But it doesn't really tell us much about the platinum group elements, because the platinum group element contents of komatiites and basalts are not greatly different generally. So this is where we're going to come into this equation down here. This is the R factor equation, and I'll just explain a little bit about how we get there. So here's the this is the equation that this was from a paper first published by Ian Campbell and Tony Nolders in the late 1970s. The variables here, this one, Y iron sulfide, that's the concentration of the metal. That's what we're plotting in those previous diagrams, what we call the tenor, the concentration of the metal in the sulfide. X I here, that is the original concentration of the metal in the silicate melt before the sulfide formed. The original concentration in the silicate melt. This thing here, D, that's the partition coefficient. And the partition coefficient is just the ratio of the concentration in the sulfide to the concentration in the silicate when they're at equilibrium with one another. It's just a simple ratio, partition coefficient. And then this number here, R, this is the proportion of the silicate to the sulfide melt. So it's the silicate to sulfide ratio. So a very high value of R means we've got a lot of silicate, tiny amount of sulfide. A very low value of R means we've got a small amount of silicate and a lot of sulfide. And if we put these two equations together, the mass balance, which is just the conservation of mass in the system, we can't bring in metal out of thin air. The amount of metal in the system that we start with is the same that we finish with. And the partition coefficient equation, we put those together, that gives us this equation. And what that means here is that if we now go back to our little sort of conceptual idea of adding sulfide to a silicate magma, here's our silicate magma, we add a little bit of sulfide to it and make droplets. If that value of R is very high, then all of the chalcophile elements, particularly the platinum group elements, which are very, very strongly chalcophile, very, very strongly favor the sulfide melt, will end up in the sulfide. But there's only a very small amount of it, so the concentrations are very high. And in fact, if you assume that the value of R is much greater than the value of D in this equation, then that equation reduces to this one, where the tenor is just controlled by the partition coefficient and the original metal content of the sulfide. Now here's the opposite situation. Here we're adding a lot of sulfide. So what's happening now is we've got a lot more sulfide melt. There's still only the same amount of nickel and palladium and everything else to go around. All of it is in the sulfide, so the concentration in the sulfide must be a lot lower. And under this situation, where we've got R is much bigger than D, other way around, so where D is much bigger than R, then our concentration in the sulfide now doesn't depend on D at all. It only depends on R. So, so the metal tenor is just purely a function of how much sulfide there is. So in this situation, we get a PGE nickel-rich sulfide. In this situation, we get a PGE nickel-poor sulfide. All right, so now let's start applying that to real rocks. Now to do that, we need to have some idea of what these partition coefficient values are. So this number D, and we've got lots of very good experimental data on this now. And here are some values for nickel and copper. And you can see that for nickel and copper both, they're very dependent on temperature. So the partition coefficient for nickel is about 400 at a comatite at 1600 degrees. If we go down to a basalt at about 1200 degrees, that number is now 900. Similarly, copper, the partition coefficient increases as the temperature drops. These are the D values plotted against temperature here. One interesting thing just to notice in passing, some other elements that you commonly find associated with sulfide-rich rocks in nature are zinc and lead, particularly zinc. Zinc has a very low partition coefficient into magmatic sulfide. The values are around about 1. So magmatic sulfides are really good at concentrating nickel and copper, but very poor at concentrating zinc. And that's actually one of the lines of argument that's been used over many years to justify the interpretation that these really are actually magmatic sulfides. They contain the elements that have high magmatic partition coefficients, but not the ones that don't. Now, the partition coefficients for the platinum group elements, this has been argued about for a long time, but we now have some very, very reliable experimental data, particularly from Mangol and Brennan. And what they showed with the partition coefficients for the platinum group elements are very high indeed. They're much higher than they are for nickel and copper. And in fact, for platinum and iridium, they're probably in excess of 1 million. So these elements are very, very strongly chalcophile. So what we can do now is we can go back to our R factor equation and put some numbers in. So let's just start out with a typical sort of basaltic magma. And then we're going to plot the nickel tenor in the sulfide up here against the R factor here. And that's the typical sort of behavior. So what's happening is at low R factors, the nickel content in the sulfide is quite low. And as we increase the R factor up to about 10,000, the nickel content increases steeply. But then what happens above that, it maxes out. That's as much nickel as you can ever get in the sulfide, because now it's just controlled by the partition coefficient and nothing else. So that's nickel. Now let's look at palladium, where we have a much higher partition coefficient. This is what we see now. So the palladium content stays very low until we start to get R factors above about 10,000 or so. And then it increases up to about 1 million, and then in fact still keeps going. So the sky's the limit really for the palladium content in magmatic sulfides. It can go up to 1,000 ppm or more, just as a consequence of these very, very high partition coefficients. So now if we look at some typical magmatic sulfide deposits, and something should be happening here. PowerPoint is frozen for some reason. Here we go. Typical nickel copper sulfide ores form at R factors typically around about 100. Some are around about that order. So they have nickel contents of a few percent and very low PGE contents. This is Norilsk. Now, Norilsk's a bit of an exception in that these seem to have formed at very high R factors for nickel deposits. So they have high nickel contents, but they're also starting to get quite high palladium contents, up around the sort of 10 ppm or so, which is high for a typical nickel deposit. Now, if we increase our R factor again a bit further, we now get to Morensky type PGE reefs. Okay, now what you notice now is that we're in the region now where the nickel content is starting to level out. So their nickel contents aren't much different from high R factor nickel deposits, but their palladium contents are now really starting to jump up. So we're now getting up to sort of hundreds of ppm. And now when we get out into the extreme ends of things, these PGE reefs associated with chromites, then we're getting up to some really super high values here. We're getting to, as palladium, which is our sulfides can ever be, up the order of 1,000 ppm or so. But what you'll notice now, in order to do that, we need R factors of 1 million. So what that actually means is for every little droplet of sulfide, it's got to see 1 million times the mass of silicate melt. And react with it and properly equilibrate with it. So how are we going to make that happen? That's a pretty major challenge from a sort of physical point of view. So now we can, these sort of R factor models, we can plot them back on our tenor plot. You can see here. So these green lines are just model R factor curves for a couple of different starting compositions. The green one there's for a mafic magma, purple one's for a komatitic magma. And what you'll see is in terms of copper and nickel, we can get into our typical sort of range of compositions with R values anywhere up about sort of 1,000 or a little bit more. But to get to going over to the palladium plot, to get to our very high PGE values, again, as I showed you before, we need R values of sort of 10,000, 100,000. And that's an R of 100,000 there. And you can see that it's just barely reaching these really chromite-rich sulfides. So it looks like there must be something else going on to allow us to make these really unusual, anomalous PGE compositions. So now let's have a look. Let's have a little bit of a look at that, and let's have a look in a bit more detail at what these sulfides actually look like in things like the Morensky reef and the UG2 chromite. So we're going to pick apart some of these rocks and look and see exactly where the platinum minerals sit in relation to the sulfides. Because the point I need to make here again, I need to take you back to the assumption that we make when we draw these tenor plots, which is that all of the platinum group elements were originally present in the sulfide. Now, we don't actually really know that. We assume that that's the case because we know the partition coefficients are very high. But what's the actual evidence in the rocks? So that's what I want to show you in the next few slides, using a technique of microbeam XRF mapping. So, and we're going to look at three case studies. We're going to look at, the Morensky reef. We're going to look at the UG2 chromite, which is a massive chromite seam that contains very large amounts of platinum group metals. It's a mine for platinum group metals and major source. Actually contains more platinum than Morensky reef does. And then we're also going to look at another interesting case, and that is the case of these very unusual platinum group element-rich chromatites, which turn up in Ophilite complexes. And the one we're going to look at particularly is one from the Shetland Ophilite. So, so you'll see why, as we go along, you'll see why I'm bringing that into the story. So again, just a reminder, what we need to do is to test that assumption that underpins these diagrams, that all of the platinum group metals were actually originally collected by sulfide. So the way we're going to do that is we're going to use this device called the Maya Mapper. Now, this is a laboratory microbeam XRF mapping system. It was designed and built by my colleagues at CSIRO. And it's developed for high definition element imaging of drill core sections over intermediate spatial scales, for drill core type sample scales. So in this case, we've actually got a slab of rock, which is about 15 by 20 centimeters. And we've made an element map of this slab of sample, which is actually a nickel copper ore from Nova, where we've got basically a chemical analysis on a 20 pixel grid. So I'm not sure how many pixels there are in this image, there's millions. But we've got a chemical analysis of every 20 pixel spot on this grid. And then typically the way we present the data is that we present them as false color maps. So in this case, we've got nickel in the red channel, we've got iron in the green channel, and copper and silica in the blue channel. And that gives us these beautiful sort of mineralogical maps, which are very, very useful for many purposes. But as we'll see here, particularly for looking for platinum group minerals. Right, so just before I show you the data, just most of you obviously know this, but just to remind you a little bit about the Bushweld Complex. So it's the world's largest layered intrusion. It's about 300 by 400 kilometers, about 10 kilometers thick. And here it is in map view. There it is in not to scale cross section. It's basically a very, very large, very, very extensive sill. It's not a funnel shape as people commonly draw it. It's a big sub-horizontal sill. This purple line around here, this is the Marinsky Reef, which is continuous all the way around the western lobe, all the way around the eastern lobe. And it's essentially the same rock wherever you see it. So you can look at the Marinsky Reef here, you can look at the Marinsky Reef here, and they look pretty much exactly the same, give or take a few small differences. So this one layer is remarkably continuous or remarkably persistent. The layer underneath it is actually the main chromite layer. In between that one and that one is the UG2 chromite seam, which is also incredibly persistent, found in both the western and eastern lobe, continuous for hundreds of kilometers and exactly the same wherever you look at it. Now here's a piece of the Marinsky Reef. This is actually a different sample, but it shows the structure very nicely. So this is a very typical example. The bottom of the Marinsky Reef usually has this sort of undulating kind of feature. These are actually, if you look at this in 3 dimensions, these things are actually like egg cartons, little holes and hills in this footwall rock, which is an anorthosite. It's a thing called a mottled anorthosite. These things here are big pyroxene oikocrysts. It's getting ahead of me. And typically the Marinsky Reef consists of this unit of a very, very coarse grained, what's sometimes called a pegmatoidal, a very, very coarse grained pyroxenites, an orthopyroxene cumulate with interstitial plagioclase. Sometimes there's quite a bit of olivine in it as well. And at the top and bottom of it are these little skinny chromite seams, one there and one there. And on this map, this is an XRF Maya Mapper image over here on the right-hand side. You can see the colors there. Chromium is red, iron's green, calcium's blue. So the plagioclase shows up dark blue. Slightly lighter blue there is clinopyroxene. The green is orthopyroxene, and you can see it's a beautiful classic orthocumulate texture, sort of chains of touching crystals. And then here's the chromite, which shows up in orange. There's a lower seam and an upper seam. Sometimes that upper seam actually cuts down through the pyroxenite to meet the lower seam. Sometimes there's actually 4 or 5 different chromite seams within the unit. But usually the top and upper one and the bottom one. Now this lighter green color that you can see here is sulfide. So now let's just change the color a little bit so you can see it a bit more clearly. Now what I've done here is I've highlighted the sulfides in this pinky color, and the chromite shows up white. So you notice what's happening is that you've got sulfide through this whole interval, around about 10 centimeter interval. And by the way, this is the entire Marinsky Reef. So there are underground mines 2 kilometers down, which are taking out this 10 centimeter layer. It's that continuous and that rich in PGEs. There's a few little sort of elements here. So here are the 2 main chromites. There's sulfide in those. There's sulfide in the pyroxenite in between them. There's also sulfide in the pyroxenite above them. Not ready for that one yet. And there's also, interestingly, there's a little bit of sulfide in this little northosite rind sitting down underneath. And that's a little layer of pure northosite. And what we think is happening there is that this is actually a norite underneath. It's a plagioclase orthopyroxene rock. That the process of making the Merensky Reef has actually partially melted the norite. It's melted out the pyroxenite and left a slush of just plagioclase crystals behind. And then the sulfide has dribbled down from the Merensky Reef into that little mushy layer. But it stops as soon as it gets to the unmolten norite underneath. Anyway, there's a really interesting story in all of this, which we don't really have time to get into now, but I can give you a couple of references where we talk about that some more. Okay, now the great thing that the Maya mapper is good for is finding platinum group elements, and particularly for finding platinum. And what we've got here is we've just highlighted every single grain of any platinum mineral that's present in this sample within about the top 50 microns of the sample. So it's a really powerful mapping technique. And what you can see is that the distribution of the platinum group metals pretty much exactly matches the distribution of the sulfides. So that's good. So that sustains our hypothesis that it's the sulfides that's collecting all of the platinum group metals. Let's just take a look at that in a little bit more detail. Now I'll just turn it sideways so we can just get a little bit more magnification on it. There's the sulfide again, and there are the platinum group metals. Now what I'd like you to notice there is that the sulfides and the platinum correspond exactly spatially, but the proportion of platinum to sulfide within the chromite seams is much higher. So if you look there, you see there's sulfide everywhere. There's sulfide in the chromite seams, but the sulfide in the chromite seams is quite sparse and it's typically quite fine grained, just particularly compared to the pyroxenite. But if you look at the platinum goes all the way through. So the proportion of platinum to sulfide, in other words, the sulfide, the platinum tenor in the sulfide is actually much higher in the chromite seams than it is in the rocks on either side. And that's happening at a scale of a few millimeters. So that's a 5 centimeter bar there. So going from there, going over, sort of a centimeter from there to there, the sulfide tenor is changing really quite systematically. Now we looked at these rocks in 3D using X-ray microtomography, and this is the result of one of those scans. So that's the chromite there in gray. You can see the beautiful little octahedral chromites. These are the sulfides here, and the sulfides form these little sort of wetting blobs that like to partly coat the chromite grains. But they don't seem to be sort of migrating through it. They form these little isolated blobs that are separate from one another. But then if we look at those in detail, the red things here, these are actually the platinum minerals. And the platinum minerals sit almost entirely on the outsides of the sulfide. And in fact, we find that where almost all of them sit is on triple points between sulfide, chromite, and a silicate phase. They particularly like that spot. So what that's telling us is that those platinum minerals must be nucleating and growing after the sulfide has accumulated. That's a really interesting point, which is going to become a little bit more apparent as we go along. So that's the Merensky Reef. So now let's have a look at the UG2. And this is a sample of a drill core. This is not actually the UG2 itself. Like a lot of the chromite seams in the Bushweld Complex, you have a main seam, and then you have a little series of little thin, what are called leader seams that sit above it. And this drill core actually goes through the leader seams. That's the drill core. These are the chromites here in red. And now let's just blow up. This is an XRF map again. So same color, the chromite's orange, the orthopyroxene is green. The sulfide is showing up in this pinky color. And you can see the sulfide's quite strongly associated with the chromite. It leaks into the pyroxenite a little bit. And then here are the platinum group minerals. And again, you can see that all of these platinum group minerals are directly associated with sulfide. So clearly, it's the sulfide which is actually collecting the platinum group metals. But the location of that sulfide is very, very closely tied to the chromite seams themselves. There's very little sulfide and very little PGEs in between those chromite seams. Almost all of it directly associated with the chromite. Okay, so now we're going to take a little bit of a detour, and I'm going to take you to the Shetland Ophilite. The Shetland Islands are this little group of islands here right off the northeast coast of Scotland. This is actually the most northerly bit of Great Britain, most northerly island, the island of Unst. This is an Ordovician age ophiolite, which has these rather beautiful chromite seams in it. These are actually mantle rocks. These things actually formed very close to the moho, probably just a bit below. What's interesting about these ones is if you go and, this is my old friend Hazel Pritchard, who sadly passed away a few years ago. Hazel spent much of her career working on these things. If you go to the little creeks that drain these outcrops and you pan out the platinum group minerals, what you find is actually they contain large quantities of quite coarse-grained platinum group minerals, but they're typically platinum group minerals of the iridium group series. So these are mostly actually iridium, rhodium, and ruthenium, osmium minerals. There's not very much platinum in these. Some of the Shetland chromite seams have platinum as well, but most of them just have the iridium group metals. Now, this is a fairly common thing. A lot of ophiolites have this. In fact, almost any chromite that you analyze from anywhere has high contents of iridium, osmium, and ruthenium. But this particular case is a bit unusual in that the Harold's Grave chromites have very, very high concentrations of the iridium group metals, up to several ppm, much higher than you find anywhere else. And it turns out when we looked at these things, that there are actually different generations of platinum group minerals. Basically, there are two distinctly different types. One type is actually found as inclusions within the chromites, and these are typically quite small grains. And these are usually minerals laurite and iridium, osmium, rhodium alloys. And then a few other things, but laurite, which is ruthenium sulfide, is the predominant one. And this is typical of chromites all over the world. You always find this. Any chromite you look at, this will be true. What's different in this particular occurrence, this very PGE rich environment, is we also find these big composite grains of iridium, ruthenium, osmium rich sulfides, which in some cases are actually up to a couple of millimeters in size. This is actually a micro CT image, and these things most typically are sort of 100 microns or so in size, but they're aggregates of lots and lots of different iridium group minerals. And there's a little bit of sulfide in there. One of the minerals in these aggregates is actually a ruthenium pentlandite. It's a very unusual mineral. We've never seen anywhere else. So two types of PGMs. These ones interstitial to the chromites, very coarse grained, a little bit of sulfide in them, and then the minerals sitting in the chromites themselves. Now, the ones that sit in the chromites, we've had a model for these for some time, and that is this is from a paper by Finnegan et al. From 2008. And what they showed is that if you grow chromite from a magma, as the chromite grows, it produces a little reduction zone, a little depleted boundary layer around the growing chromite. And because the solubility of platinum group metals in silicate melts is very low, and it's also dependent on the redox state, within these little reduced zones, the iridium is no longer soluble, and it pops out as iridium alloy grains. And then these grains get incorporated in the chromite. So that's our first generation. Now, the second clue, this is another important paper on this topic, Fonseca et al. And what they were interested in was how you form iridium osmium alloy grains in mantle rocks. And it's quite a complicated story. So I'll just cut to the conclusion, which is that if you partially dissolve sulfide magma, so in this case, we've got rocks with sulfides in them, we're heating that up and we're dissolving the sulfide back into the magma it formed from. The mass of the sulfide liquid is decreasing. As that happens, the concentration of the platinum group metals in the sulfide goes up because the platinum metals, the osmium, iridium, whatever it is so strongly bound to the sulfide, it stays there. Its concentration goes up and up and up as the sulfide dissolves until eventually we get to the point where it actually starts to crystallize alloy phases. It starts to crystallize its own minerals. And in fact, that happens. These are some models from that paper. That happens when you've melted somewhere around about sort of 10 to 25% of the sulfide. These things will actually start to form. So that gave rise to this model for what we think might be going on in the Shetland chromite, that we're generating our platinum group metals during partial redissolution of the sulfide liquid. So we start out with a chromite with some sulfide in it. Then, for whatever reason, as that chromite continues to grow, or as the chromite seems to start to crystallize, that sulfide dissolves. And as it dissolves, it forms these osmium iridium grains. Then eventually, most of, if not all of that sulfide dissolves out completely and disappears. So that gives us another sort of like a variation on the Finnegan model, where we start out with our chromite, supersaturated sulfide undersaturated liquid. Our chromites start to grow. That causes platinum group minerals to nucleate in places, but it also causes sulfide liquid to nucleate because this layer is slightly depleted in iron. That makes our sulfide. But now, as we continue to grow, this chromite now gets flushed by sulfide undersaturated magma. That causes the sulfide liquid to redissolve, and then that leaves behind our platinum group minerals. So this mechanism, we think, might explain our observation in the Merensky Reef, where there's still lots of platinum group minerals in the chromite, but most of the sulfide seems to have gone. So that's what we think is happening here. This chromite originally had the same amount of sulfide as the rocks next door to it, but that sulfide has redissolved as the chromite was crystallizing, but it left behind the PGMs. So that then gives us, so here's our R factor model again. We need a way of getting out to this very extreme kind of R factor value out here. So what we're suggesting is the way we get right out to these very extreme values out here is that we actually dissolve a lot of the sulfide, which effectively increases the R factor. Now the environment, I'm running out of time, so I don't have time to go into this in detail, but just for those of you interested to follow up, the environment that we think this is happening in for forming the Merensky Reef or forming chromite seams in general is when we're bringing in a pulse of superheated magma into the Bushweld magma chamber. That magma actually erodes the cumulates underneath it, and that's what generates the characteristic pothole features of the Merensky Reef, which I just mentioned in passing. It also generates that anorthosite rind that I showed you in detail. And then our chromite then crystallizes on this irregular surface, but it actually grows, it crystallizes in situ, it nucleates and grows actually where you find it. And the evidence for that, this is a paper which we have in review at the moment, the evidence for that is if you look in detail at the chromite in these things, they actually form these really interesting 3D interconnected clusters, which we think are growing up from the bottom of the chamber. But anyway, that's another story. I can give you a reference to read on that if you're interested. But that's basically the mechanism that we think is generating these extremely PGE-rich chromatite reefs. So, but the reason for showing you this again is just to then hark back to this. Our assumption about the original deportment of platinum palladium in the sulfide component is borne out by these detailed grain scale observations. So we're pretty much at the end here. Our assumption is correct. This transient kinetic sulfide saturation followed by partial redissolution could explain extreme PGEs in sulfides and chromite hosted reefs. In rare cases, if we completely dissolve all of the sulfide, we might generate concentrations of PGMs with little or no sulfide, which are the kinds of things we see in some Ophilite complexes. That's basically it. So I hope that was interesting and clear. And please feel free to ask questions.
All right. Thank you, Steve. What a very interesting talk. And many ideas here and there to discuss things, I think. Do we have any questions from anyone in the audience? If you have any question, feel free to ask.
May I?
Yes.
Yeah.
Go ahead.
And thank you for presentation. It was so interesting. And I have a question. And in the in the picture of the Merensky Reef, in the image of XRF mapping,
yeah,
yes, there is a big sulfide mineral between the chromitite layers. That,
yes.
That doesn't include PGE.
Yes, it does.
Yes. And according to your instruction, the chromitite in the chromitite layer, sulfide in the chromitite layer move to that area and make bigger, I thought. What is your idea?
Okay, that's a really interesting question. Let me just put that back up again. I'll just find that slide again. I can. This one, I think. Okay, let me just share my screen again. I seem to want to do it. Oh, hang on, sorry, I can't get to share my screen. I don't know why.
Am I supposed to click on something? Let me see.
Yes, you might have to give me permission again.
I think now the condition.
But anyway, just while we're trying to. Oh, here we go. I've got it now. Right, you should have it now. Okay. Yeah. Okay. Yeah. So let's get the pointer back. So you're talking about these big sulfides over here.
Yes, yes, yes.
In this very coarse-grained peroxenite in between the two chromite seams. In fact, this is very typical. So everything about this rock here is actually exactly the same as this rock over here, which is the one that sits on top of the upper chromite seam. Everything is the same. The mineral compositions are the same. The proportion of sulfide is the same. The proportion of platinum to sulfide is the same. The only thing that's different is in this little layer here, it's much coarser grained. And the interpretation that most people give for this is that they think that there's been a buildup of water in the intercumulus liquid in this little layer in between the chromites. And that causes this rock to recrystallize. And that makes the sulfides also effectively bigger because they've got more space to sit in between the crystals. So the reason the sulfides are, of course, grained here is really because they're sitting in the pore space between the silicates. But because the silicates are much bigger, the pore spaces are also much bigger. So it's really just a matter of geometry. But the other interesting thing, I don't think I can actually, I'm not sure if I can show you. Let's see if I can. It's not only the sulfides that are coarser, but also the platinum group minerals themselves are much coarser. And there's actually one very big, it's actually that one there. There's one very big platinum grain in there. It's actually a platinum sulfide grain. And in fact, that one grain contains something like 25% of all of the platinum in the entire sample, if you do it's like sort of a 3D volume correction for it. Now exactly why that is, we don't really know. So here we are. So here we are in 3 dimensions. So this is in the chromite, but these big ones in here actually have much bigger platinum grains. There's fewer of them, but they're much bigger. Now, what is actually causing that, we really don't know. But it seems to be some sort of secondary recrystallization process. Now, I'm sure you know there are lots of arguments about whether hydrothermal processes have been involved in concentrating platinum in the Mariinsky Reef. I'm very much of the belief that they don't have anything to do with concentrating the platinum in the first place, but they do have something to do with the final texture of the rock. So I think that's what we're seeing there, that it's very much a second order process. It's not doing anything to really concentrate the platinum. It's just moving it around at a very fine scale.
Thank you very much. And in my sample, the eastern limb of the Bushweld complex and northern part of the eastern Bushweld, my sample doesn't have extreme chromitite layer, and the pegmatidal pyroxenite texture in Mariinsky Reef. So I thought the texture is a little bit different from this sample, and I will observe more according to your explanation. Thank you very much.
Sure, no problem.
So Steve, I also have a question which is partly related. So you're showing that you have lots of PGEs in these little grains, and even single grains can have an effect on the sample concentration of platinum, for example. So does it mean that the sulfides are less enriched in platinum compared to what you would expect from, let's say, distribution coefficients?
No, not really. If you sort of work out the ratio of sort of platinum to sulfide, even on the scale of those little individual layers, they're all still very, very strongly PGE enriched. They're all still, very, very extreme tenors, but they're just even more extreme in the chromatite, and specifically directly right in the chromatite. So now there's another idea which has actually been around for a long time now, which was proposed by Tony Noldrett, which was that the sulfides and the chromite actually react together. And that there's a process which is to do with the crystal structure of the spinel structure of the chromite. It often has defects in the lattice, and those defects somehow interact with the sulfides and cause degassing of the sulfur. So the sulfur moves off into a volatile phase. I can find the reference for that. It's an interesting idea, but it's never really actually been supported experimentally. There's not really any actual sort of direct observational evidence that it can happen. But it could be another mechanism, and it would explain the observation in the same way as to why you would get these extreme ratios of PGEs to sulfide just directly in the chromite seams and not immediately outside. And it's obviously a very, very fine localized control, because you can see the scale it's operating at. It's on a scale of a few millimeters.
And looking at these images, also one thing that is surprising to some extent is that you have such small grains that are supposed to scavenge elements from a wide area. So yeah. I'm not sure if one could expect, let's say, gradients at the sample scale in terms of PGEs.
That's one of the real sort of important problems in explaining these things, how you actually attain these very, very high R values. So the small size of the droplets is actually, that helps, because if you've got a very small droplet, it's got a high surface area compared to its volume. So it's actually more reactive. The more surface you've got, the more reactive a droplet is. But you've still got to get that droplet to interact with a very large volume of magma. So, and there are really two ways you can do it. One way is you can actually suspend that droplet in a convecting magma and then pull it out again. So I settle it out or mechanically segregate it. It would take too long to go into the arguments in the time I've got, but Rais Latipov has written a string of papers about this. Actually, I'll put his slide back up again. Let me just share. Oh, you're still showing my screen, yeah. So this is Rice's model. And an important observation here is that when you look at the Merensky Reef in detail in potholes, you often find that basal chromite seam actually undercuts the layers. So this over here, if you can see my pointer, but over here in the bottom right-hand corner, that's actually pretty accurate what the Merensky Reef does. It actually drapes over topography, and sometimes that topography actually undercuts the layers above it. But that chromite's always there. The sulfides are still there, and the PGEs are still there. And typically there's less sulfide, and the tenors are a bit lower, but it's still always there in this setting. So what that says is that this chromite must actually be growing at that contact. And the sulfides must also be growing at that contact. They're not settling out. So what they must be doing is actually interacting with a convecting layer of magma, so that the magma above is actually interacting with and crystallizing that. Now, a point I didn't make, and I should have done, is that, let me just go back a slide. So to this one, one of the things about chromite is that chromite's actually very insoluble in basaltic magma as well. So you can only dissolve a few hundred ppm chromium in a magma before it makes chromite. So to grow a chromite seam, it actually has to be growing from a large volume of magma. It has to be growing from probably about 1,000 times the volume of magma as the actual chromite. So if you've got, so if the chromite is reacting with 1,000 times its own volume, and then sitting within that chromite, you've got a tiny proportion of sulfide, I say 1% sulfide. That sulfide's also got to be seeing the same amount of magma. So if the R factor for the chromite is 1,000, then the R factor for the sulfide is 100,000. Because it's the same volume of magma, but a much smaller volume of sulfide. So the same process that makes the chromite is also what's generating the high R factor for the sulfide. And if you believe Latipov's story, which I think has a lot of good evidence for it, then it's basically convection of the magma in the lower part of the magma chamber that's making that happen. I'm sure people working on the bushveld will know, I'm sure there's a lot of controversy going on at the moment, particularly around whether some of these critical zone layers are actually in place as younger sills into the pre-existing stratigraphy. There've been a number of papers, Jim Mungall and a few other people, James Scott, published high-resolution TIM states where they claim that the Morensky Reef is actually younger than the rocks above it, and that it must have been in place as a sill. And the problem with that is that the cross-cutting potholing relationships between the successive layers clearly show that it can't be. So the bastard reef, which is the layer that overlies the Morensky Reef, actually forms potholes that cut down through the Morensky Reef in many places. So it has to be younger. So there's something very funny about those zircon dates that nobody's really explained yet. But also none of those models goes anywhere towards explaining, well, why are these, how do you get these super PGE rich sulfides, and how do you make the chromite? Where's the volume of magma you need to make them? So without going too far down that rabbit hole, I'm very skeptical about these models.
Yeah, I think that supposedly the whole thing happened quite quickly, right? So every time you try to give an absolute age to any part of the system, then you're always playing over a narrow range of time. So it's easy to be swapped, right?
Yeah, that's right. These interpretations all depend on these TIM states having error bars of sort of plus or minus 200,000 years. And the TIMS people say they do, but you know, there's something not right somewhere. Sure. Something's not. If it's not fitting with the geology, then there's got to be something wrong.
So maybe the precision is very high, but we are not too sure about the accuracy.
Well, it's really the precision that matters actually in that case, because if you're dating a whole lot of layers by the same method, and they're all supposedly very precise dates, then it's the relative ages that matter. But there's still, it's not resolved. That's an ongoing argument I think we'll be having for a while. And it's an important argument because it goes towards the whole issue. There's a broader argument going on in the petrology community about whether magma chambers exist at all. There've been a number of papers by people like John Blundy, Steve Sparks, Kathy Cashman, arguing that there's no such thing as magma chambers, that all of these things like the Bushweld Complex are actually just multiply in place thin sills, and there was never a large volume of magma there in the first place. In fact, Rice Latipov and I have a paper in review at the moment where we're arguing that that can't be right, because chromite seams prove that you have to have large volumes of magma, however you do it, whatever the exact mechanism is. The mass balance requires that they've got to be large volumes of magma present all at once in order to make these features. So, but anyway, that's ongoing. Lots of things we still don't understand. Yeah. Something I often say at the end when I give talks about layered intrusions, I'll put a question up at the end under a challenge. So can you tell me one thing that everybody who works on layered intrusions agrees on? And almost nobody can. There's almost nothing about layered intrusions that everybody who works on them agrees on. Right down to the most sort of fundamental things about what they are and how crystals form and all the rest of it, which is a bit depressing, given that we've been working on these things since Wager and Brown in the 1950s. 60 years. You think we could agree on something by now, but no.
No, let's say that makes a good subject for for people starting to study these things nowadays, right?
Yeah.
And they have quite a lot of work ahead. So they
Yes,
know
sure.
what they can do in the next, 30 years, 50 years, and so on. And there's also one thing, just as a general comment, like you said, the understanding is that most of the sulfur is external, right? It doesn't come from the magma itself. This is because of solubility considerations. You need to get the sulfur in from some surrounding sediments, essentially, right? That would be the source. Yeah,
well, that's true more for the sulfide-rich nickel-copper dominant deposits.
Okay.
Now, in the case of the reef-style deposits, the answer is actually we really don't know. And the problem is that when you've got very high R factors, the sulfur isotope signal gets mixed out. So it doesn't help you. So there's, it may be that the sulfur in the Bushweld complex is externally derived. We just don't know, and there's no way to tell. And it may be that in some of these layered intrusion situations, in some it's definitely true, that the sulfide liquid is forming just as a result of fractionation of the magma. The magma just fractionates until it hits the sulfur saturation surface, and then the sulfide liquid comes out. But in almost all of the cases we know about, except for maybe one or two, there's no real doubt that the sulfide has to be coming from external sources.
Okay, so in these cases, then there is an obvious link between, let's say, the massive sulfide, nickel and copper and PGA deposits, and what was happening with the sedimentation and the sulfide deposition in a sedimentary environment, right? So you need sediments, and so you need erosion of emerged land, right? So that is all, let me see, it's dependent on surface processes, right? And now
I guess that's true to a point, but so there are a couple of things there. One is that we think that the sulfide liquid droplets can actually be carried quite a long way because magmas flow through the crust quite fast at sort of, tens of centimeters to meters per second kind of rates. Whereas sulfide droplets would actually could actually be carried a long way at those kinds of flow rates before they settle out. So, which means that the source of sulfur doesn't actually have to be the rocks that are the immediate wall rocks of the intrusions. It can be a long way away, and in a number of cases, it almost certainly is. So that's part of that story. The other point I was going to make. Well, also there's often a big difference in age between the intrusions and the sediments that they sit in. So, for example, the Bushweld Complex is in Archean sediments, the Transvaal supergroup. So there's hundreds of millions of years between the age of the sediments and the age of the intrusion, and that's true in lots of other places too. So particularly deposits that are intruded deep in the crust. It's not always true. Sometimes the ages are quite close, but usually there's a fairly substantial age gap. So there's a lot of geological history that involves just having sulfide somewhere along the path. The other interesting argument that's going on at the moment is we've always assumed that sulfides are being generated at depth and then they're carried up and then injected from a magma which is flowing upward through the crust. But there's actually quite good evidence in a number of places that sulfides are actually being placed downwards. And there are a couple of places where we know that's true for sure, Sudbury being one. And that then goes to the physical properties of sulfide liquids. And the sulfide liquids are quite remarkable things. They're very, very dense. They're also super low viscosity. They've got viscosity less than water. And also they've got enormous heat capacity. So what you've got is a dense, hot liquid which can penetrate any crack that you like and carry a lot of heat in with it. So sulfides can actually melt their way into country rocks. And in many of the deposits we've looked at, we see really clear evidence that's exactly what's happening. But in some places, they're melting the country rocks and moving 10, 20, 30, 40 meters off the contact. The deposit we've just been working on, the Nova, a beautiful example of that. And the sulfide's actually the agent for melting the country rocks. And in fact, the sulfides might actually be the thing which is actually creating the space for the intrusion. So the sulfide comes along ahead of the intrusion and the intrusion develops after it. And that's a really, very sort of different kind of concept from what we've had for many years about the origin of these deposits. So we're still learning all sorts of new things about them. And particularly by coming at the problem by trying to understand a bit more about the physical processes, trying to understand the physics of how these liquids interact and work with one another. And that's been something that's been a bit neglected over the last few decades. We understand the chemistry really well, but the physics is much less well understood, and it's really important to understanding the deposits. Sorry, what was the question?
Yeah, no. I was just thinking that the whole thing is it's quite fascinating, and so understanding how these things are emplaced and the two coexisting liquids, how they basically interact. I think that's probably one of the most fascinating aspects. Yeah. Any more questions from anyone? Anyone in the audience? There's also one little technical curiosity I might ask you about that. You're showing all these beautiful chemical maps that you do with micro-XRF.
Yeah.
So you basically use polished slabs, right? So how?
No, just a cut slab. You don't need to polish it.
You don't need to polish. Okay, so the polishing basically doesn't make any. Does it make any effect on the quality of the final images? Or
not really. No, not much. No.
Not much. Okay.
The one advantage with polishing probably is that with the rough cut, you perhaps actually lose some grains off the surface. So if they're like sort of minor platinum grains that are sitting right on the surface, you might maybe cut them off. And polishing might reduce that effect a little bit, but I've never really noticed any significant difference. We haven't tried it systematically to see what difference it makes. We probably should. But one of the big advantages of the method is you can just take drill core, just cut drill core, or just a slab a sample off the rock saw. It doesn't even have to be that finely cut. I usually just clean it up with a little bit of sandpaper just to get any rough material off the surface, and that's what all of those images were made with. That's all you need to do.
Yeah,
it's a really powerful technique for these rocks. It's like having a giant thin section.
That's right.
A giant thin section with an element map on top of it.
That's right. Yep. So any more questions? I think there will be tons of things to discuss in reality.
Well, look, feel free to drop me an email if there's anything you want to follow up on. I'm happy to respond to emails. I'm just, I think my email's on the final slide. Yeah, there it is. steve.barnes@CSIRO.au. So yeah, just drop me a line. I'll be happy to help. But the final slide there also, there's QR codes to a couple of the papers. And again, yeah, if you have trouble getting them, let me know. And I can send you copies.
Yeah, that sounds fantastic. So I don't know, at this stage, I guess that if we don't have any immediate questions, maybe we can finish the lecture here. So thanks, Steve. Thanks a lot for coming and talking to us. Maki-san, do you have any final remarks or things you want to say?
So we will upload your presentation on YouTube, so that everyone can check your contact and everything.
Yep, sure, that's fine. Yeah, just send me the link. So I'll put a link to it on our website as well.
Thank you very much.
Okay, no problem. Well, thank you all for listening, and hope your research on the Bushweld is very successful. We wish you all the best. And yeah, email me if you want to know any more. Okay.
Sounds perfect.
Thank you.
Bye. Thanks, everyone.